Friends, let us continue our discussion on chemical kinetics, and in our last session we defined the rate of reaction. So, we have a reaction summation nu j equal to nu j aj equal to 0, that is our standard reaction, and we define rate for a closed isothermal constant pressure system as rate of change of extent of reaction, that is d alpha dt, normalized by the volume of the reacting mixture. I mentioned in my last class that if you are dealing with homogeneous reactions, this V is the volume of the reacting mixture, but if you are dealing with heterogeneous reactions which involve more than one phase, the normalization could be by several different ways. For example, if you are looking at gas solid catalytic reaction, then the normalization could be by the volume of the catalyst or by mass of catalyst. So, appropriately we will define rate as d alpha dt 1 over W. W for example is the weight of the catalyst that we are using. We know our extent of reaction is defined as Nj minus Nj0 by nu j, and so if we take a derivative of alpha, we can now define rate of change of species j as 1 over V d Nj dt, and as we saw in the last class that R and Rj are related to each other, or nu j into R is simply Rj. So, now let us continue our discussion further and try to see what kind of mathematical expressions we can expect for rate of reaction. So, let us consider the same reaction, and now our objective is to find out how rate depends upon the operating conditions. Recall that in our discussion on thermodynamics, we talked about how equilibrium constant and therefore extent of reaction depends on operating conditions. Now, our objective is how this rate depends on operating conditions, and we could choose various different ways in which we could express this dependency. For example, if it is a gaseous phase reaction, then I could choose temperature, pressure and mole fractions of all the components. And if I am dealing with mole fractions, we know that they all should add up to 1. So, we have mole fractions of only n minus 1 component, that is our reaction has n component, let us say, or to be specific, let us say it has 3 components. Then we need to specify mole fractions of only 2 components, because the third one will be determined by the fact that y1 plus y2 plus y3 or all mole fractions should add up to 1. In other words, if we have n components, we need only n minus 1 mole fractions. If we do not like mole fractions and we want to deal with concentrations, for example, we could choose rate to express rate as a function of temperature, pressure and concentrations of n minus 1 species. Once again n minus 1, because when it comes to looking at concentrations, we know that there is an equation of state for gaseous components which will relate temperature, pressure and total concentration. Simply put, PV equal to nRT, and our concentration is nothing but n by V. So, there is a relation which defines the total concentration. So, we can choose any n minus 1 component, the other one is automatically fixed. Or if we do not like even that, then we could simply choose rate as a function of temperature and concentrations of all the components. So, pressure does not explicitly appear now, because that is now inbuilt in the form of expressing concentrations for all n species. It is this last form which is quite common, particularly for reactions involving liquid solutions. For gases, the first expression is more common, either in terms of mole fractions or partial pressures, because if you look at partial pressure is nothing but mole fraction into total pressure. So, any one of those forms. But if you look at any of these expressions, the total quantities that appear are n plus 1, that is n is the number of components plus 1. So, it could be either T p plus n minus 1. So, 2 plus n minus 1, again n plus 1, and so on. So, now let us look at some of the common forms of these rate expressions, and the most common form is the power law kinetics. So, let us look at the most common form of reaction rate expression, namely the power law kinetics. Now, what is power law kinetics? Power law kinetics is, simply put, rate is proportional to concentration of species 1 to the power q1, concentration of species 2 to the power q2. So, product of all the such C1 raised to q1, C2 raised to q2 up to Cn raised to qn. In a compact form, we can express this as rate equal to k, k is that proportionality constant, product of Cj raised to qj, j going from 1 to n. So, qj is the order of the reaction with respect to species Aj, and this is the simplest form of power law kinetics. Now, we call this qj as order with respect to Aj, and if you sum up all these qj's, we get q, what we call as overall order. Let us take few examples and see what are the various possible orders that are possible. So, what are the values of q that we can have? So, let's take few examples. Let us say that we have a reaction of, let me make it little darker. Okay. So, we have a reaction of hydrogen iodide getting decomposed to H2 plus I2. Now, it turns out for this particular reaction, the rate of reaction is proportional to concentration of hydrogen iodide raised to power 2. So, clearly in this case Q is 2, there is only one species in the reactant side. So, our Qj and Q are same. So, this is the order of the reaction. So, Q can be integer. Let us take another example, decomposition of acetaldehyde to give us methane and carbon monoxide. Now, it turns out the rate of this reaction is proportional to concentration of acetaldehyde raised to power 3 by 2. So, Q in this case is 3 by 2, or in other words, orders can be integers, they can be even fractions. Do they have to be positive numbers? Not necessarily. For example, if you look at the reactions such as oxidation of carbon monoxide to carbon dioxide, under certain conditions for this reaction the rate is proportional to concentration of carbon monoxide raised to minus 1, or in other words, the order now is Q is minus 1, that is can be negative numbers. So, the point that I am trying to make is q can take any value. Quite common to have positive numbers, but also there are cases where q can be negative. In fact, quite often the power law kinetics is actually something which is fitted to the observed rate of reaction, and when you do any numerical fit, there is no guarantee that q can be only in integers or positive numbers, negative numbers and so on. So, q can take essentially any of these values, that is positive number, integers, fractions, negative numbers or even 0. That is, if rate is proportional or rate is proportional to concentration of a species raised to power 0. So, q can be 0. What it means is that rate is actually independent of concentration. There are few real cases, we will see examples of few of them, that under certain conditions the rate is actually independent of concentration. So, the order of reaction, actually let us revisit order of reaction. What is order of reaction? Now, if you say that I am going to define, I am going to just do it with respect to two species, because same thing can be said with respect to any more number of species. So, if I say that my C2 raised to Q1, C1 raised to Q1, C2 raised to Q2, I can write this by taking natural log, let us say, of both sides as ln r equal to ln k plus Q1 ln C1 plus Q2 ln C2. So, in other words, I can write my rate expression by taking logarithm of both sides, left hand side and right hand side, and now if you look at this expression, I can write Q1 is nothing but del ln r del ln C1, or in other words, my Q1 is the differential of ln r with respect to ln C1. Now, for a true power law kinetics, this is what I get. Now, there are quite often situations where my rate is actually not power law kinetics, but something which looks of this type. That is, when I have some complicated function k C1 C2 divided by 1 plus K1 C1 plus K2 C2 and so on. Even for these cases, I can define my apparent order or observed order with respect to C1, with respect to C2. How do I do that? I know for my exact power law kinetics, definition of order is this, that is Q1 is ln r del ln r del ln C1. So, for any other rate of reaction such as this, I can take ln r, I can take derivative of ln r with respect to ln C1. This is then defines, if I do that for this particular function, what is this del ln r by del ln C1? It is also nothing but C1 by r del r by del C1. That is my definition of del ln r by del C1 ln C1. So, I can then take derivative, for example, of this particular rate function, and then with respect to C1, and whatever normalize it by C1 by r, I will get apparent order with respect to species C1. I will get apparent order with respect to C2 if I do the same exercise with respect to C2, that is C2 by R del C2. So, these are all what are called as apparent rates of reactions. Now, this is as far as the rate power law, simple power law kinetics is concerned. A specialized case of power law kinetics is what is called as law of mass action kinetics. This mass action kinetics or law of mass action kinetics is again a case where these orders are related to stoichiometry of the reaction. So, for example, if Qj is half of difference between mod nu j and nu j, then we say we are the reaction follows law of mass action kinetics. To give you an example, and this is just an example illustration, not real kinetics. For example, going back to our methanol synthesis, if we have reactions such as CO plus 2H2 gives rise to CH3OH, our general power law kinetics can be rate equal to K, some kinetic rate constant, concentration of CO raised to Q1, concentration of H2 raised to Q2, okay, and in general concentration of methanol raised to Q3. So, I am calling this species 1, 2 and 3. So, what we have is a general power law kinetics, this particular representation for this reaction. What is our nu 1? Nu 1 for this case is -1, nu 2 is -2 and nu 3 is +1. So, if Q1 according to this formulation is half of mod of -1 -1, there is a mistake, this should have been plus, yes. So, that would give us Q1 is 1, then similar thing would give Q2 is 2 and Q3 is 0. So, if that is the case, then our kinetics would simply look like rate equal to K into concentration of CO raised to 1, concentration of H2 raised to 2, or in other words the order and molecularity are same, and that is what is the law of mass action kinetics. Let me repeat that in law of mass action kinetics, the orders are same as the stoichiometric coefficients or corresponding nu j's, and for product it is 0. I think I should stand corrected, what I had written earlier was the right one. Okay. That is Q1 is half of mod -1 minus -1. So, that is 1, Similarly, we will get Q2 as 2 and Q3, that is any product term will have no influence on the rate of reaction. So, this is our law of mass action kinetics. Now, let us look at how rate of reaction depends upon the temperature. Now, in earlier slide we said that there is a rate constant K, and it is a common practice to express rate constant K as a function of temperature. In fact, our earlier discussion on thermodynamics also told us that equilibrium constant also depends on temperature, and for certain reactions equilibrium constant will also appear in our kinetics, and that also then becomes the rate the function of temperature. Now, the dependency of rate constant on temperature was initially observed, and an expression for this observation was provided by Arrhenius way back in 17th century. And what experimentally people had observed even before Arrhenius gave this mathematical expression was that rate constant. So, what we are seeing here is the rate constant on y axis as a function of temperature, and rate constant increases as temperature is increased, and in fact increase is exponential in nature. Arrhenius, by using the arguments of activation energy, proposed that this relationship can be expressed in the form of K equal to A e raised to minus E by R T. That is the rate constant K is at the frequency factor A exponential minus E is the activation energy by R T, R universal gas constant, T as temperature. Now, what was his idea in proposing this kind of rate expression? He argued that if we have, let us say, a reaction of the kind that A goes to, let us say A plus BC goes to AB plus C, that is just an hypothetical reaction. And so, if we now monitor or follow what happens to the energy of the system as the reaction proceeds. Reaction is proceeding from the reactant side to the product side. So, x axis is representing the progress of reaction, y axis is representing the energy levels. So, at the beginning of the reaction we have reactants A and BC at certain energy levels. At the end of the reaction we have products AB plus BC, and for these reactants to go from A and BC to AB plus C, some energy barrier has to be overcome. There are various people have given various explanations. For example, a transition complex such as A, B, C is formed from A plus BC, and then this complex breaks down to give you AB plus C, and in formation of this complex an energy barrier has to be crossed, barrier of the magnitude EA or the activation energy, and unless this barrier is crossed the reaction cannot proceed, and hence the rate of reaction is dependent on temperature in this particular manner. That is his idea. That is the idea. There are various other theories of slight modification, but this was Arrhenius when initially he proposed it. It is a purely empirical relationship. Now there is a transition state theory, collision theory and so on, where the dependency is slightly different. In fact, in a more generalized form, the dependency can be written, that is K is proportional or rather proportional to t raised to power, let us say n, t raised to power n e raised to minus e by r t, where n can be 0, 1, half, depending on what framework one is developing for looking at the activation energy. But I want to point out another interesting aspect, that what an exponential rate actually implies. Now, the same information that we saw earlier, that this K increases exponentially as we increase the temperature. Let us put it slightly differently. Let me expand the scale, or rather let me make y axis natural log to actually see what is happening here. So, what we see here is, for example, when temperature is 300, I have used certain activation energy, the rate constant is 1.6 into 10 raised to minus 3. So, this is my rate constant. If I increase temperature by 10 degrees, that means close to 3% increase in temperature. What happens to my rate constant? Rate constant also increases, but the increase is not as dramatic. Let us say from 300 to 310, the rate constant becomes 0.0035. But let us see what happens if I increase my temperature by 100, that is 33%. So, increase in temperature is only 33%, but look at what has happened to my rate constant. The increase is now 2 orders of magnitude or 100 times, and this difference goes on widening as we increase the temperature, or in other words, because this temperature dependency for rate constant is exponential form, it is a highly non-linear dependency. That is, small increase leads to a large increase in rate constant, which if we come in this domain, we can see from here to here the rate constant has increased significantly. Now, why is this crucial? This is crucial because when you are operating reactors, and let us say that you are designed everything to operate in temperatures in this range, for some reason your temperature controller fails, temperature starts increasing, the temperature increase may not be dramatic, it may be 10% or 20%, the rates of reaction increases quite dramatically, 2 orders of magnitude for less than 1 order of magnitude increase in temperature, or in other words, there is a significant increase in rate of reaction, and you never know what will happen if rate of reaction goes uncontrolled. So, this is why control of temperatures is crucial, but this also illustrates another aspect, that in design of reactors, when we are dealing with kinetics, even for first order kinetics or when q is 1 the order, we could have significant non-linear behavior because of temperature variation in the system. Let me reiterate, if I say my rate constant rate of reaction is K C1 raised to 1. So, a first order reaction. We all know that first order reaction implies linearity of rate and concentration. However, even though rate and concentration are linear as it appears in this expression, the rate constant K is dependent on temperature in a non-linear manner, such as shown over here. Now, as we will see later on, in a reactor, concentrations and temperatures do not change independent of each other, at least if you are talking about, let us say, adiabatic reactor. So, if we are talking about adiabatic reactor and let us say exothermic reaction, then concentrations and temperature are related to each other. So, in other words, even though the kinetics is first order as it appears, there is an indirect influence of concentration on the rate of reaction. Direct influence is through this C1 over here, indirect is because K depends on temperature and temperature is related to concentration. So, this indirect effect is felt here. So, even for simple first order kinetics, we could have dramatic effects in terms of how reactor behaves. We will see those examples, but origin of those effect can be seen even for simple reactions like this. Now, coming back to our activation energy complex, if we say that this is a barrier, higher is the barrier, higher is the barrier, higher will be the energy that will be required and lower will be the rate constants. What is activation energy? If we mathematically look at the expression for K, K is A e raised to minus E by R T. So, ln K is ln A minus E by R T, and if we plot ln K versus 1 over T, the slope of the line is given in the form of slope of the line gives us the activation energy. So, this slope is now nothing but E by R. Just as we talked about apparent order when we talked about reaction rates which do not necessarily follow power law kinetics, but we can define apparent order as ln R, the partial of ln R with respect to ln C1. We can also define the activation energy or rather apparent activation energy when R does not necessarily follow a simple power law kinetics. For example, if you have a rate expression which looks something like this, K some kinetic rate constant times concentration divided by 1 plus some equilibrium constant K1 into C. We will see where those equilibrium constant is coming, and this is where I said there is a possibility that equilibrium constants also appear. This actually appears for a lot of gas solid catalytic reactions. So, if we have something like this, then we know K is a function of temperature, capital K1 or this equilibrium constant is also function of temperature. So, there is nothing like single activation energy, because both of these are function of temperature, but we can define apparent activation energy or minus E by R, and what will that be? Recalling the same exercise that we did for apparent order, it is now del ln K or ln R divided by del of 1 over T. So, we can define now recall that R is K into C. So, if this was my kinetics, del ln k del 1 over t would be same as del ln r del 1 over t, because ln r is nothing but ln k plus ln c. So, derivative with respect to 1 over temperature of r and k will be same, and this is what is used in finding the apparent activation energy. Why these apparent order, apparent activation energies are required? As we will see later on, not just for this kind of reactions, but reactions where transport is important, we find that rate of reaction actually may not be given by the kinetic rate expression such as this, but it may involve transport processes, diffusion, mass transfer rate. So, rate of the rate may be actually governed by the diffusion rate, for example. Now, diffusion rate, dependency of diffusion rate processes on temperature is much milder than the dependency of kinetic rate constants on temperature. Kinetic rate constant on temperature is exponential, as we saw here. So, what happens when you take a derivative like this? You get an activation energy value which is fairly low. In fact, if diffusion process is independent of temperature, then the activation energy or the apparent activation energy for such process would be 0. So, when it comes to making some judgment whether processes are transport related or transport controlled or kinetically controlled, a good rule of thumb is to look at the activation energies, and if activation energies typically 40 kilocalories per mole to 100 kilocalories per mole are typical of any chemical reaction. But if values are much lower than that, that indicates that it is not the kinetics, but something else that may be controlling the process. Let us now come to reversible reactions. That is, what we are saying is, we have a reaction, let us say A1 plus A2 gives rise to A3 plus A4. So, we have now a reversible reaction, and reaction can go from left hand side to right hand side or right hand side to left hand side, and so rate of this reaction R now involves components from the left hand side to right hand side of the reaction. We call this reaction as forward reaction. So, this is my forward reaction, and that is left hand side to right hand side, and this is my backward reaction. From right hand side to left hand side. So, I have a rate given as rate of forward reaction minus the rate of backward reaction, then the total rate, because there is something going from A1 to A2, that is forward, something going from A3 to A4, that is reverse. We can express both forward reaction rates and backward reaction rates as power law kinetics, and we have, for example, if you choose Rf as product of Cj raised to Qj and the forward rate constant Kf, Rb as product of Cj raised to Qj prime need not be same as Qj over here, and the rate constant Kb. So, the net rate of reaction is the product of Cj raised to Qj, Kf into that product minus Kb into Cj raised to Qj prime. Once again, law of mass action kinetics is a special case where Qj is half of mod nu j minus nu j, and Qj prime is half of mod nu j minus mod nu j plus nu j. If you take the same reactions A1 plus A2 going to A3 plus A4, I can write for law of mass action kinetics Kf C1 C2 minus K backward C3 C4, and you take the generalized power law kinetics Qj prime, put the appropriate value of nu j's, you will find that this is what the rate we get, and this is what is the law of mass action kinetics for a reversible reaction. Now, there are several aspects of reversible reaction that we should be worried about or concerned about, and let us go to a specific example to see this particular aspect. So, let us say that we have our reaction A1 plus A2 giving rise to A3 plus A4. Okay. We wrote this reaction rate as R equal to Kf, and I am in general going to write C1 raised to Q1, C2 raised to Q2 minus K backward C3 raised to Q4 and C3 raised to Q3 and C4 raised to Q4. We are considering a reversible reaction, and we are interested in seeing what happens to this rate of reaction as this reaction approaches equilibrium. If you recall, when we discussed about thermodynamics, we said the following, and I want to bring that once again, that for this particular reaction we will have the constant Kc, the equilibrium constant, which is e raised to minus delta G0 by RT. Delta G0 a thermodynamic property. So, given temperature this Kc is fixed, which is nothing but C3 C4 divided by C1 C2. Okay. This is my true thermodynamics. This we saw in our last class. Let us visit that equilibrium in a slightly different manner. When this reaction is taking place, what happens? We have forward reaction rate, which is this Rf, and we have reverse reaction rate, which is this Rb. Now, when equilibrium is reached, the process simply comes to a halt, the net process comes to a halt. We also talked about what is actually happening is at equilibrium, this forward rate of reaction is counterbalanced by the reverse rate of reaction. So, if that is the case, then what is the rate at equilibrium? At equilibrium rate must be then 0. So, the net rate is 0 or Rf is equal to Rb. Now, if we take this kinetic interpretation of equilibrium, and I want to stress here, the condition of equilibrium is free energy change is 0. This is not the condition of equilibrium, this is a consequence of equilibrium. One often gets confused between what is the condition of equilibrium, and when I normally ask this question in my class, I get two kinds of answers. One, the correct one, which says that the free energy change must be 0, and one which is incorrect, which says that rate of forward reaction is rate of backward reaction. It is incorrect in the sense that the true condition is this is a consequence. So, we cannot say that this is the condition of equilibrium. Okay. So, if you have rate of forward reaction same as rate of reverse reaction, then if we put this, we get the following: C3 raised to Q3, C4 raised to Q4 divided by C1 raised to Q1, C2 raised to Q2, because this particular rate is equal to this particular rate. What is this equal to? This is equal to K forward divided by K backward. Now, recall that K forward and K backward are kinetic rate constant. We know at equilibrium, the equilibrium constant maintains certain relationship between the concentrations. In this particular case, K3 C3 C4 divided by C1 C2. Since both conditions we are looking at same equilibrium, there has to be consistency between these two. For example, my equilibrium constant Kc is now Kf by Kb. What does it imply? It implies the following, that if I have a reversible reaction, then I do not have freedom of choosing Kf and Kb arbitrarily. Whatever may be the value of Kf and Kb, the ratio of 2 must be the equilibrium constant, which is already predefined for me from thermodynamics. So, this is from thermodynamics. So, if I estimate a value of Kf, then my Kb is automatically fixed, because the ratio of 2 has to be equilibrium constant. So, I do not have that freedom to choose Kf and Kb independently. I could choose Kb independently, but then Kf is fixed. So, it is a same story. Further, you look at this ratio, which is C3 C4 by C1 plus C2. So, Q1, Q2, Q3, Q4 are also cannot be randomly chosen. For example, a simplest case we can choose is the following. Let me remove all these things. So, we can choose all Q1, Q2, Q3, Q4 as unity, and then this will become C3 C4 divided by C1 C2, which is Kf by Kb, which is constant Kc. In fact, what it means is I cannot have Q1, Q2 let us say 1, Q3, Q4 as 2, because that would mean that this particular relationship is not consistent with our thermodynamic definition of equilibrium constant. So, there is a restriction on how we can choose Q1, Q2, Q3, Q4. In fact, it turns out for a general power law kinetics, we can they need not be actually all unity. We can say that as long as the ratio of, so for example, if I am defining my as long as my ratio of Qj by Qj prime divided by the stoichiometric coefficient nu j is some constant C, a non-zero constant, but this is same for all species, I am okay, the thermodynamic consistency is followed. So, we should ensure that for a general reversible reaction, if we are framing a power law kinetics of this kind, firstly Kf and Kb cannot be independently chosen, because there is a thermodynamic restriction, and secondly the orders Qj and Qj prime also cannot be independently chosen. There is a restriction that Qj minus Qj prime divided by stoichiometric coefficient uj has to be some constant, non-zero constant. 0 would not mean anything. So, it can be 1, minus 1, half, minus half, whatever you want, but as long as it is same for all species, that is for species 1, 2 up to all n species, as long as this ratio is constant, we are not violating the thermodynamic consistency. We will stop here for the day and look at how this rate changes as the reaction proceeds, because to have it is important to have some qualitative understanding of how rate of reaction changes as reaction proceeds. So, this will be the topic of discussion for our next session. Thank you.